What's up, Raiders? Just want to go through some of our one-dimensional motion problems. Now in each class, we've already solved a slightly different combination of these problems. So you can find some of these problems already in a posted PDF in Google Classroom. But for both classes, I want to go through some of the other problems that we did not get a chance to take a look at yet. And in each class, we've already solved all the problems on page 1, so we'll move on to page 2. Okay, so looking at number 5. A sports car accelerates from rest to 90 kilometers per hour in 6 seconds. What is its average acceleration in meters per second squared? Well, right off the bat, we can see we've got a velocity expressed in kilometers per hour, but we're looking for an acceleration in meters per second squared, so we're going to have to be consistent with our units. And we've talked about the fact that length or distance or displacement in physics, the base unit of measurement is meters and time is seconds, so we're going to convert that velocity of kilometers per hour to meters per second. So I'll explain this a little more thoroughly in this first problem, but then after that, any subsequent conversions of velocities, I'll just kind of go through them more quickly. So if we've got our velocity expressed in 90 kilometers per hour, express that as a fraction here. It's really 90 kilometers for every 1 hour of travel. So the conversions that we're going to be using here, the conversion factors are 1 kilometer is equivalent to 1,000 meters. 1 hour is equivalent to 60 minutes. And 1 minute is equivalent to 60 seconds. Those are going to be the conversions that we're going to use here. And it doesn't matter what order you do these in, as long as you do them correctly. So we've already got our distance or displacement expressed in kilometers in the numerator. We want to get rid of that. So to cancel it out, the next place that kilometers need to show up is in the denominator. So 1 kilometer is equivalent to 1,000 meters. That would express our velocity right now in meters per hour. But we don't want time expressed in hours, we want to get rid of that, and it's already in the denominator, so the next place hours need to show up is the numerator. 1 hour is equivalent to 60 minutes. Now our velocity is expressed in meters per minute, so there's one more step to go. 1 minute is equivalent to 60 seconds. So now we've done what we need to do in terms of the setup so that our velocity will be expressed in meters per second. So going across the top here, 90 times 1,000 times 1 times 1 is 90,000, and the only units left are meters, which is what we want. And then the denominator, 1 times 1 times 60 times 60 is 3,600, and the only units left in the denominator are seconds, which is what we want, meters per second. So it turns out 90 kilometers per hour is equivalent to 25 meters per second. So now we're ready to move on with the rest of the problem. A sports car accelerates from rest to 90 kilometers per hour in 6 seconds. What is its average acceleration in meters per second squared? So let's identify what information we're given in terms of our equation variables. A sports car accelerates from rest, so that's its starting situation, so the initial velocity is 0. And notice I didn't call it just plain old v for constant or average velocity, because we're told the car accelerates, so it starts at this velocity but it ends up at something different. So the initial velocity is 0, and the final velocity expressed in meters per second, it's going to reach a speed of 25 meters per second, and we're told the time is 6 seconds, and we're trying to find the car's acceleration. So using the problem-solving technique, we've identified what information we're given in terms of our equation variables, what we're trying to find. The next step, take a look at your equations and see if you have a relationship that connects this specific combination of variables mathematically. And sure enough, we do. VF equals VI plus AT. The final velocity of an object equals its initial velocity plus the product of its acceleration rate and time, how long it's been accelerating at that rate for. So we're looking for accelerations. We're going to have to rearrange this equation a little bit. So I'm going to subtract initial velocity from both sides. So final velocity minus initial velocity equals acceleration times time. Now finally divide both sides by the time. So the acceleration, now we have that variable isolated, so now we just substitute our values in. So final velocity minus initial velocity is our numerator. over the time of 6 seconds. So this ends up being approximately 4.2 meters per second squared. So notice, just to kind of reduce the visual clutter, I did not include units in my calculation, but make sure that you, like always, you include the appropriate units in your answer. Okay, moving on, number 6. At highway speeds, a particular automobile is capable of an acceleration of about 1.5 meters per second squared. At this rate, how long does it take to accelerate from 75 kilometers per hour to 100 kilometers per hour? So we got the same situation that we had last time. We have units that we need to kind of get consistent with other units in the problem. So we're going to convert these velocities of 75 and 100 kilometers per hour to meters per second. But since we just went through that a little more elaborately, that approach up above, I'll show the work here, but I'm going to do it a little more quickly. So 75,000 meters per 3,600 seconds works out to be approximately 20.8 meters per second. Do the same process again for the velocity that you end up at, 100 kilometers per hour. So we have 100,000 meters covered in 3,600 seconds at this rate. So that works out to be approximately 27.8 meters per second. So now that we've done those conversions, now we're ready to just apply the problem solving technique here. So our given information, if the car goes from a velocity of 75 up to 100 kilometers per hour, so they laid out for you pretty cleanly what the initial and final velocities are. The initial velocity is approximately 20.8 meters per second. The final velocity is approximately 27.8 meters per second. And we know the car's acceleration rate, also given to us, is about 1.5 meters per second squared. And we're trying to find time. So with our problem-solving technique, we've identified the information we're given in terms of our equation variables, what we're trying to find, and then you look at your equation list, see if you have something that ties together the specific combination mathematically. And notice it's the same one we have up above, we just happen to have a different unknown. Now we're looking for time. So we still have that same relationship, VF equals VI plus AT, but now we're looking for T. So subtract VI from both sides. VF minus VI equals AT. Now we're looking for time, so divide both sides by acceleration. And this time will be equivalent, approximately equivalent to the following calculation. Final velocity of 27.8 meters per second minus the initial velocity of 20.8 meters per second. And that's divided by the approximate acceleration rate of 1.5 meters per second squared. So this gives us approximately a time of 4.7 seconds for this to happen. All right, in another video, I'll solve some more problems. As always, if you have any questions, contact me on the Remind app.